Good evening, here yet again with another lovely session of CENG 3325 Structural Analysis. This is the 11th lecture in the video series, and today we're going to be looking at the final way of solving or finding shear and bending moment diagrams, and that is V&M diagrams by inspection. So we're going to be looking at shear and bending moment diagrams by inspection. So V and M diagrams by inspection. So shear and moment diagrams by inspection. Okay, so shear and moment diagrams, we have looked previously at two methods. We have looked at using the method of sections, where we cut a beam at some point and reveal the internal forces and then solve for those as a function of x. We have looked at integration, where we solve for, we first get the load functions, then we integrate and apply appropriate boundary conditions. And finally, V&M by inspection. This is a more area-based method, where we start with our loads and we just apply the relationships that we already know in terms of shear and moment. And we work through it to get our ultimate shear and moment diagrams, ultimate loads, etc., etc. So it's based on a few fundamental principles. These are based on some fundamental principles, on the following principles. One, just how we've discussed previously, that reactions at the left side of a beam, for example, cause an upward jump in load, or reactions cause upward jumps in the shear diagram, I should say, or how couples or point moments cause changes in the moment diagram. If we really know what we're doing, we can actually use these relationships to directly get the entire shear and bending moment diagram. Now, for more complex loadings, for example, if you have a really complicated loading, like a parabolic loading or a really interesting sinusoidal loading or something like that, something bizarre like that, method of inspections really isn't something that you want to use very frequently, but you might want to use more of a integration approach for a very complex loading function. But for something that maybe has a lot of different zones, or for something that maybe, okay, for example, if you had a beam that had several different zones, but each zone was itself fairly easy or fairly simple, that is where the method of sections really shines. So anyway, we're going to have a few basic principles. First, vertical loads shift shear diagram up or down. We'll shift the shear diagram up or down. Up or down. Of course, up being positive and down being negative. So in other words, an upward load, including an upward reaction, an upward load or reaction, that looks like the word bad, an upward load or reaction yields a upward jump in the shear diagram. And then the downward load does the opposite. Downward load reaction yields a downward jump, or downward movement, or whatever you want to call it. Downward drop. There, that's right, noun there. Down drop, or downward drop, in shear. 2, concentrated moments cause jumps in the M. Concentrated moments or couples, really the same thing, different words for the same thing. Or concentrated moments / applied couples cause jump in M in the M diagram. And this one is a bit interesting, and it's because unlike this one does correspond where an upward reaction causes an increase in the shear, and really that's because of the negative we had in our equation before. So with this, it's a little bit interesting in that a counterclockwise moment will cause a negative jump in the moment diagram. counterclockwise applied will equal a negative drop in moment diagram. And the way to think about this is, while the exterior load applied to a beam may be positive, or maybe in the positive direction, it would cause a negative drop in the internal forces. And then clockwise applied, this will equal a positive jump in moment. Let me show you what I mean by this. Let's consider a cantilever beam. And a cantilever beam will work well because a cantilever beam here will work pretty well simply because we have that's something I can have an isolated end. So let's consider a cantilever beam with a end moment applied. Let's apply an end moment to this. So if we apply an end moment to this, this is a positive external moment. It's a counterclockwise external moment. But what happens if I were to cut this, say like right here? Let's cut out this section and see what that looks like. Let's cut that section out and see what that looks like. Well, this section of the beam, assuming there are no other loads on it, I would have the external moment, which would be counterclockwise or positive, but the internal moment, this internal moment here, this internal moment is negative. So look, negative internal moment. Now, this particular section would still be in positive bending if I ignore anything else on here, but the point being that an external moment needs to be resisted by something. A positive external moment is resisted by an internal negative moment. External moment applied will be resisted by a negative or a clockwise internal moment. By or positive external, I should just say moment M, I got a little confused here, getting ahead of myself, is resisted by an internal negative. So all we need to remember is that, this is a long-winded explanation of something relatively simple to apply, that if we ever have a concentrated moment, if we're applying a counterclockwise applied moment, that's going to cause a downward drop in the moment diagram. If we apply a clockwise, it's going to cause a positive jump. What else? We have end conditions to be aware of. We have a few end conditions to be aware of. 3 end conditions. If there is a free end, for example, A here, a free end with no applied force or moment, well, at that end, let me describe 2 of these, and then we also have the pin ends. Pin ends with no applied moment or applied point moment. And I'll write this in red for emphasis. So if you have a free end with no applied force or moment, at that point, say for example on a cantilever end, the M will be 0 and the shear will be 0. And if you have a pinned end with no applied moment, here the M will be 0. And we've talked about that at great length already in the previous videos on this. And then finally, a 4th principle that we're going to be using, the 4th here, is that we need to remember, if I can spell remember properly, remember. Let us consider our description here. V is equal to the negative integral of w of x, the negative integral of w of x dx, and M is equal to the integral of v of x dx. Or in other words, What are these? What is an integral? Obviously, the derivative will give you the slope of a line, but fundamentally, these are referring to areas. These are area functions. Like all integrals. Well, maybe not all integrals, but most friendly polynomial integrals is functions of x. So in other words, the area under shear, or under the load diagram, gives change in shear. And in turn, the area under shear gives change in moment. In moment. And finally, maybe 0.5 here. Maybe a 0.5, just a final note. Fundamentally, if you have, well, the functions, especially polynomial functions, and then maybe that will be important in an example we're going to work through, we'll move to higher orders. So it's very common to have polynomial loadings. It's very rare to have anything other than a polynomial loading, like we could have a sinusoidal loading or something. I gave that an exam once. That was fun. Anyway, polynomial loadings will move to the higher orders. In other words, if your load is a linear function, you take the integral of it, the shear move to higher, let's say, orders. Yeah, that's what I want to say. Move to higher orders. So in other words, if your load is a linear function, then your shear will be a quadratic function, an order of 2. If your load is, and then in turn, when you integrate that, you would get a cubic moment function. So we have all of this. These are our basic principles, but the easiest way to really demonstrate this, like in many cases, is by example. So let's work through an example. And I'm going to work through 2 different examples of applying the method of inspection. So example 1, let's consider a simply supported beam with a constant load applied at the middle. And this is going to be a very good one for the method of sections, and we'll see why in a second. So consider a simply supported beam, and let's say there is a uniform load across here. Like this here, and we'll make it even nice and symmetric. So we have a uniform load of 20 kilonewtons per meter, doing this one in metric just for fun. And let's say it has reactions AX, AY, and BY. And of course, AX is going to be equal to 0 in this case. Then I'll go ahead and draw some dimensions on this. This is going to be 4, 6, and 4. 4 meters, 6 meters, if I can write M properly, 4 meters, 6 meters, and 4 meters. And so this is a given, and we want to find, this is given, and we want to find the V and M functions, or V and M diagrams. Shear and moment diagrams. Truth be told, the shear and the method of inspection really isn't the best if you truly want the shear and moment functions. If you want functions rather than just a diagram, really in most cases the method of sections or the method of integration are going to be superior. But anyway, so let's just work through this solution, and we're going to work through a series of steps. So step 1 is going to be to find the reactions. Now I could do this any number of ways, but I'm actually going to apply a really clever and simple method here, and that is I'm just going to say, oh wait, first AX has to be equal 0 because there's no horizontal force, And then 2, apply symmetry. Both the geometry and the load are symmetric. So I can say that AY must equal BY, which must equal 20 kilonewtons per meter times 6 meters divided by 2. This is symmetric, so therefore AY must equal BY, and therefore these must equal 60 newtons upward. Oh, actually, sorry, this should not be kilonewtons, this is newtons, sorry about that. 20 newtons per meter, a little typo there, or hand-drawn typo. So 60 newtons, so this is a very lightly loaded beam. Now, what I want to do is, I really want to be clear, I want to make sure to draw a really nice free body diagram for this. When working through the method of inspection, you really need to come back and draw another free body diagram. And I would like to go back and think about, how would I solve this using, say, integration? This would not be terribly difficult, but it would be quite involved to do this via integration. See, I would need to divide this into 3 different sections. One from here to here, another from here to here, and a third from here to here. And I would need to find functions for each. Well, the load functions are going to be easy. The load function here would just be 20 and 0 and 0. But I would still need to integrate twice in each region. So I would need a total of 6 integrals. And I would need to do the method of boundary conditions. It would need to apply boundary conditions for this end and this end. I could use the fact that I know the shear at the either end. And I could also, but then I would need to use for this one the boundary condition of this region to get the one in this region, as we did in the second portion of lecture 10. And as we saw, that can be quite involved. It takes quite a bit of time. I mean, it would take quite a bit of time to do that, depending on how quickly we move through it. This is one, though, because the load function is so simple, because we have the load functions here are incredibly simple. We have just no load here, we have a constant value load here, and no load here. This is really ideal for a method of inspection. So here, got that stuck. So step 3, or step 2 here, I'm going to draw a good free body diagram. Now, let us consider the free body diagram. I'm not going to draw the, any of the pins and reactions, or sorry, pin and roller. Instead, I'm just going to show the relevant forces. So I have a 60 Newton force here, and a 60 Newton force here. Then I have a 20 kilonewton per meter force here, distributed across the middle. Or I keep saying kilonewton, the 20 Newton per meter. I'm used to beams having loads more like kilonewtons. It's like seeing a load, if you saw a load in English units as, 5 pounds per foot, that wouldn't be a very typical beam. So this is a very lightly loaded beam. That's okay. So we have end A and end B. And then dimensions, let's say this is 4 meters, 6 meters, and 4 meters. Now, we're just going to go ahead and directly get the shear diagram. I can get the shear diagram without doing a single cut for sections. I can get the shear diagram without doing a single integration, get a single load function. All I have to do is apply the principles that I saw previously. Now what I'm going to do is I am going to do some trace lines like I do like to do sometimes. I'm just going to draw what I call trace lines, which now if you were doing this on grid paper or graph paper, sometimes I would still make these, but especially on a blank white canvas like this, it's very nice to have something that'll keep everything reasonably lined up, so I don't have to eyeball it. So I'm just going to put 4 trace lines down like this here. And like this here. Then the shear diagram, step 3, I'll just have the shear diagram and label that the shear diagram. So I'm going to have my 0 axis here. And let's say this is the load. This would be my W. And then let's say I have my shear V as a function of X, or maybe I can just say W and V. And V, this would be in, let's just say this is in newtons. Okay, the first thing I'm going to do is, well, I'm going to use red for consistency. The first thing I'm going to say is, look, at the start of the shear diagram, this 60 Newton force is going to cause the shear to jump up to 60. Going to cause a jump up to 60. So I know initially this thing's going to be at 60. 60 newtons. Now, from here to here, do I have any load? Think about that. The only thing that's going to change the shear is if I have any sort of load from here to here. I don't, so I know that shear must be constant from here to here. Again, I have no load from here to here, from the reaction to the start of the distributed load. Therefore, the shear must be constant. Now, from here to here, what can I realize, or what can I see? I do have a distributed load, which means I have an area, and the area under this is going to be 6 times 20, which is a total of 120 newtons. So what that means is, again, we've discussed previously, and we've mentioned previously in this lecture and in the previous lectures, that the area under the load is going to give us the change in shear. So what that means is that as we go from this point to this point, the total area under this, of course, is 120. So that means we're going to drop by a total of 120. And 60 minus 120 is negative 60. So that means we're going to be down here at negative 60 newtons. Now, I know I'm going to go from I'm going to go from positive 60 to negative 60. And then the only question is, what form of equations that take? Is it like I mean, I can think of all sorts of equations I could draw. I could draw something like this. I could draw something really funky like this. I could draw almost any kind of function I could imagine. So how do we actually know the general shape of the equation, of the curve that connects this? Well, we apply calculus. I know this is a constant value function. What is the integral? What is the integral of a constant value function? Well, it's a linear function. So I know this thing is going to drop as a linear function. And I would like to draw a straight line if I can manage that. Not too bad, better than the previous attempt. So I know this is a linear function between here and here. Again, because the integral of a constant value function is a linear function. So because the load is a constant value function, the shear is going to be a linear function. Then from here to here, I don't have any load, so therefore the shear is just going to be constant. And then finally, the reaction at NB is going to cause the shear to jump up by 60, and it will go right back to 0. And that is the final shear diagram. That's it. I didn't have to do a single cut. I didn't have to solve a single function as I didn't have to solve for a single thing as a function of x. I didn't have to do any of that. I could directly get the shear diagram. Again, for more complex loadings, this doesn't work too well, but for more simple loadings, this works quite well. Now, I am going to realize this is going to have a couple areas, so I'm going to label a couple areas that we're going to look at later, or actually right now. I'm going to call this and this area 1, and they're going to be equal magnitude but opposite direction. This is going to be a positive area, this is going to be a negative area. Then, and I want to find the area of this because we're going to need that for the moment. So I know that area 1, what is the area of this? Area 1, well, I can just say 60 newtons times 4 meters is going to be 240 Newton meters. Then let's get area 2. I'll go ahead and do this in another color. Maybe don't have any light green on there, so or maybe purple for something different. So this area here, and this area here, this triangular area, let's call this area 2 and area 2. Again, equal in magnitude but opposite direction. You don't have to do the area off to the side, but it's easy to illustrate. It's useful to illustrate for this problem. And this is just going to be the area of a triangle, 1/2 base times height, 1/2 of 3 meters, times the height of 60 newtons. And so notice, this works very well for things where you can very easily calculate the area. So for example, if you have a If the shear was for example, parabolic, well, or something even more complex like sinusoidal or something, if I want to find the area under a sine graph, I'm going to have to do an integral. And if I'm going to have to do an integral, I've kind of eliminated the entire point. I'm kind of missing the entire point of doing the method of inspection. The entire point of it is trying to avoid taking integrals and working with functions in the first place. So if I have something really simple like a constant value function, maybe a linear load or something like that, maybe then it makes sense to use the method of inspection. But if I'm going to have to do a bunch of integrals anyway, just to find the areas under the curve, I'd probably just be better off doing the solving by integration anyway, or using method of sections or something like that. But anyway, this will come to, quite simply, this will come to an area equal to 90 Newton meters. Meters times newtons, it has units of Newton meters. And then finally, step 4 is going to be the moment diagram. Step 4 is the moment diagram. Diagram here. And I think I'm going to put another trace line because I have two different areas here. I'm going to put a trace line from this 0 point. Because if you think about it, from here, this area here is going to make the moment more positive. This is going to make it more negative. Again, we know that moment is going to be affected by shear, and the area under the shear is going to indicate the change in moment. So let's consider our points here. Now, first of all, where do we start? Well, this is a pin and roller simply supported beam. So I know that the moment is going to start and really end at 0. So I could put the 0 point right here, but let's actually use that as a check. Let's make sure we end up back at 0. And if we don't, we know we did something wrong. So let's look from here to here. I know that from this point to this point, we're going to increase by the moment is going to increase by a value equal to the area in this box here, in this region here. And we already calculated that as equal to 240. So we know that we're going to be up here at 240. 240. And let me just put a label here as M. Maybe I'll do that in black to match the other ones. So change that to the color black, change my pen. M in Newton meters. Here. And so we know that from here to here, we're going to increase by 240, which will produce, since we're starting from 0, will produce a final value of 240. Now, it is very important to keep in mind, and remember always, that the area under this is not going to give us the value of the moment. It's going to give us the change in the moment. It's a calculus thing, a fundamental theorem of calculus. Now, since we started out at 0, the change will put us at 240, but again, area will give you the change in the area under the shear will give you the change in the moment, not the actual value of the moment. But anyway, we know the value here, and we just have to ask, again, what kind of function is it going to be from here to here? And that's going to be fairly straightforward. We have a constant value function. The integral of a constant value function is a linear function. Oh, I missed that line. Reasonably decent linear function. So I might even put a L here to indicate a linear function. Not a bad idea for sketches, just a little something to indicate that I have a linear function. Now, from here to here, I'm going to increase by a total of 90 Newton meters. And if we started at 240, when we increase by 90, I know that I'm going to end up 90 plus 240 is going to be 330. 330. Now, I have to ask, what is going to happen to the function? What kind of function is going to be? It's not going to be a linear function. It's going to be a parabolic function or a quadratic function. So I know that this is a linear function here. The shear is a linear function. The integral of that is going to be a parabola or a quadratic function. So the only question I then have to ask, is it going to be like this or like this? Which is it going to be a concave up or a concave down parabola? Well, I can think I could put in test points or take the derivative or take the integral if I wanted to, but I can, since all I'm looking for is a sketch here, I can say, look, I know that shear is the derivative moment. So the shear is going to, at any point, the value of shear should be the slope of the moment. And at this point here, I have a value of shear of 0, which means at the peak of this point, I should have a horizontal slope, which means this has to be basically a concave down parabola. So something kind of, oh man, I need to, having trouble drawing parabolas today, so something kind of like that. And if I wanted to do this very clear, if I want to do this ideally, the end slope here should match the initial slope of the slope of the linear function. And then from here to here, this is also going to be parabolic, and it's going to drop down the same area, negative 90, and 90 minus, or 330 minus 90 is going to be 240, so we're going to drop down to 240 here. Very misshapen parabola, but oh well, just a quick sketch. Then from here to here, we're going to drop down the area equal to area 1, and 240 minus 240 brings us right back down to 0. So I'm going to go ahead and put some notes on here. Maybe that this is a parabola, B for a parabola, and maybe L for a linear function. And we can recognize this is going to be positive throughout, which means we have positive bending, which looks like this, or our actual beam is going to be bending like this all the way through. A few other notes here, notes to keep in mind. A few other notes. We of course saw that when dm of dx, when the derivative of this is going down, we know that v of x is going down or decreasing. So the value of the shear is getting more negative. When the derivative or the slope of moment is decreasing, then the shear is decreasing. And that's how you can tell if you're concave up or concave down. And also, note here, when v of x is equal to 0, this is again just basic calculus, but it's good to remember. And note, when v of x equals 0, dm dx is equal to 0. Therefore, m is max or min. Is max or min. And so you can see that this is a fairly straightforward and relatively quick way of solving for shear and moment diagrams. Okay, let's work through another example. Maybe I can look at a cantilever beam, and we can see, and if you really want to see the difference, I would encourage you to try to solve through these, also using the method of sections or the method of integration, to really compare how different and how quick the method of inspection can be if you really got the hang of got the hang of it. I'm trying to combine got the hang of it with got a handle on it. That's not good. So example 2. I want to give an example that has some nice point moments and point load on it. So consider this, and let me call this example 2. Example 2. So consider this cantilever beam here. Here. And I'm just going to go, for the sake of expediency, I'm just going to go ahead and draw the reactions on here. I trust by now you know your statics and you can solve for the reactions here. So you have we're going to have point A and point B. So given this, now I wouldn't normally give you the reactions, you have to solve that, but for the sake of time, I'm just going to go ahead and draw these out. And let's just say the reactions were given, but really I would expect you to be able to solve for them. So let's say we have a 100 Newton meter end moment, a 40 Newton midspan moment, and if just these were given, you would find that we had reactions. Now we know what because A is a free end, so there's no reactions there, but B is going to have both a X force, a Y force, and a moment. Now we have no horizontal load, so the X force is 0. But what we will have is we'll have a vertical force, a vertical reaction force, By, and if you calculate that, well, that's actually fairly straightforward. that is going to be 40 newtons. That should be fairly obvious why that is, just sum of forces in the vertical direction. But if you go and calculate the moment, you will actually find that the moment is actually clockwise, or a negative moment applied, and this comes to 300 Newton meters. You can get that by solving for the moment about point B here, or point here, or the midpoint, whatever you might need. And the only other thing we're going to need is the, basically I call that MB equals 300 Newton meters. And the other things we need are our dimensions. So normally I would only give you the loads and ask you to find the reactions, but for the sake of time, I'm just going to give them to you here. So we have that, and then we want to find the full shear and moment diagram via inspection. Find V and M by inspection. So I'm just going to draw this directly below here. We already basically have our free body diagram. I could redraw it. Actually, you know what? I am going to go ahead and do that for simplicity's sake, so I can have everything nice and lined up. And I can replace the, it just creates a little cleaner diagram. So this is my free body diagram, or you could also consider this our load. And here, let's go ahead and put our loads here. I have my 100 Newton meter on the left side, my 100 Newton meter couple, my 40 Newton point load, and my reactions at B, which would be 300 Newton meter, and 40 newtons. And I think I'll go ahead and do my favorite trace line technique, where I like to show some just light vertical lines. I usually pick a very light color that won't clash much with my other markings. And it's not going to be perfectly straight, but it does show, at least I'm intending for everything to line up. Like this here. So let's get the shear diagram. And I have one other example I want to work through after this, and it will show how to incorporate something known as a hinge, which we have discussed previously, a hinge or a moment release. Let's see here. So let's get the shear diagram, V, and let's say this is in kips, or sorry, newtons, not kips. Now, it's important to keep in mind that moment, if we apply an end moment to this, that's going to cause a jump in the moment diagram, but it's not going to cause any kind of jump in the shear diagram. So initially, there's basically no vertical load on this thing. A couple doesn't produce any vertical load. It does produce a moment, but it doesn't produce any vertical load. So from here to here, our shear is 0. From the let me go ahead and put our dimension. We have 10 meters here and 10 meters here. So from end A to the midspan, we have exactly 0 shear in the beam. Then at this point here, we do have our first vertical load, and that's a point load. And we know from previous cases, from our previous example, that a point load is, or maybe from our previous discussions, an example, that a downward point load is going to cause a downward drop in the shear diagram. So we start at 0, and we're going to drop down 40, which means we'll be down here at negative 40. And then there is no vertical load from the center span to point B, and so our shear then is constant. Nope, that didn't look horizontal enough for my taste. And then finally, the end reaction is going to cause an upward jump here. So nothing too bad, negative 40 here. Now I want to get the area, negative 40 newtons here. I do want to get this area, and conveniently this is the only area we're going to need to get for this problem. Relatively simple problem, I know, but it's just meant to illustrate how you work with things like point loads and point moments. So let's call this area 1. And area 1, well, it's just a rectangle. Area 1, it's not like my circle there. Area 1 is just going to be equal to negative 40 newtons times 10 meters, which comes to negative 40 Newton meters. So that area is going to cause a drop from here to here of negative 40 Newton meters. And then, so we could label these as steps. Did I label, let's see. Well, I'll just call this, step 1 would be finding the reactions. I kind of already gave that to you. So let me go ahead and do that solution. I'm sticking with my classic given find solution format. 1 is get reactions. I already did that. I breezed through that to just get that really quickly. 2 would be the free body diagram. 3 would be the shear diagram. And 4 would be the moment diagram. I'm going to go ahead and label this as having units of Newton meters. Newton meters. Then I have my 0 axis. And, okay, so I need to find my starting point for my moment diagram. So I start here at 0, and I'm going to jump up I'm either going to jump up or down. I know this couple is going to cause a jump in the moment. What do we do? And it's oh so tempting. It's oh so tempting to say, look, this is a negative moment. It's a clockwise moment. Therefore, the moment is going to drop because negative is clockwise. Not quite right. As we really have, repeatedly discussed, and we discussed at the beginning of this lecture, the moment diagram is going to change by the opposite of the applied moment. So this is a negative moment, so that means this is going to increase by 100. The internal force, or the internal moment, is going to be opposite the applied moment. So if we're applying a negative, we get an internal jump in the positive direction. So this is going to jump up to positive 100 Newton meters. So it jumps up to positive 100. And then looking at this from here to here, I have no applied moments. I don't have any applied couples from here to here. And normally that doesn't prevent us from having a change in the moment because normally you have some sort of shear. But looking at this, I have no shear from here to here, from here to here, from the left end, from the free end to the midspan. I have no shear. So that means I have no area under the shear curve, which means the moment is going to be constant. Another way to think about this is a 0 function, and the integral of the shear function is a constant value function, so it shouldn't surprise us that we have a constant value function from here to here. Then the area under this, from the center span to the support over to point B, is going to have an area of negative 40. It's under the curve, so it has an area equal to negative 40, which means we are going to drop down by negative 40. Although, wait, did I get that right? This does not seem quite right. Oh, I can't math properly. That's why. It's like, that doesn't look right. That was a slight error on my part. Error is human. 40 times 10 is not 40. Indeed, it is negative 400. I need to go back to grade school and read my multiplication. 40 times 10 is 40. I'm getting all philosophical here or something. Anyway, so we start at 100, and then we're going to drop down to 40. We're going to drop down by 400. And if we drop down by 400, if we start at 100, that means we're going to drop down to negative 300 here. And then we can ask ourselves, okay, well, what form is that equation going to take? Well, I know the integral of a constant value function like this is going to be a linear function, so that means we are going to drop down as a linear function. And if we wanted to, we could solve for that point just by using any number of methods. If we were concerned with where the moment was equal to 0, we could solve for the that x point, and that actually would be useful, especially when we get to deflection. We'll see that later in a week or two. Now, of course, then our end moment here, I kind of got ahead of myself. This end moment is going to be negative, which will cause a positive jump in the moment diagram, which will bring us back to 0. And one way to think about this, the moment diagram, it's going to be positive in this region, which means the beam is going to be bending, something like this. Positive here, like that. And we're going to have an inflection point. We have an inflection point where the beam will go from concave up to concave down. And here, the beam will be bending downward in nice, sad negative bending. Or just negative bending if you prefer. Negative bending like that. And that will be our final shear and moment diagram. So you notice how quick and easy this is. Again, this only works really well for relatively simple loadings, but if you do have a case with relatively simple loading, like something like this, getting the shear and moment via an integral is really a pain in the butt, or not really necessarily a pain in the butt, but definitely more than you need. Definitely more than you need. Okay. So the final thing I want to look at is more advanced case of shear and moment diagrams, something I usually don't cover in statics, but I do think it's important for structural analysis because it's going to be very important when we get to frames. And that is how you handle a hinge when doing shear and moment diagrams. So hinge. A hinge or a moment release is hinge, basically, let me list all the names for this. This has a lot of names. Hinge / internal pin / moment release. Okay. So how do we handle this? First, what this looks like is something like this. If you have a something like that where two members come in and there is a hinge in the middle of the beam, and it might look something like, you could have something like this, the fixed beam, although this wouldn't necessarily be statically determinate. You could have something like that, something kind of like that, something where you have some sort of hinge in the middle of the beam. But what does this do to the shear and moment diagram? How can we solve this by an inspection? Now, if you're doing method of sections, this isn't too bad, but if you're using a method of inspection, you really have to know how a hinge or an internal pin or moment release, these are not different things, these are just different names for the same thing. Principles to apply. What happens here? One, there is no jump in the shear at the hinge, unless there is a point load on the hinge. We're talking about purely the hinge itself. Two, there is no jump in the moment. So in other words, the pin, by definition, is going to be able to transfer shear right through it. So if you, unless you have a point load on it, in that case, you could have a jump in the shear, but that would be a jump caused by the point load, not by the internal pin or via the hinge. So if, in other words, if your function here shows that your shear was 20 kips here, it would have 20 kips on this end as well. And we'll also have no jump in moment at hinge. However, we have to think about this back to our pin example that we looked at previously. If you have a simply supported beam, well, if you have a simply supported beam, what did we remember about the moment at each end? We knew that because it had, because the beam had, because that joint could have no, because that joint could have no moment. We knew that the moment had to be 0 at that hinge. And really the same thing will hold true here. We know that the moment is going to equal 0 at a hinge. So that's really the third thing. The moment's going to equal 0 at a hinge. So the moment must equal 0 at a hinge. So I'm going to work through a longer form example, but this will be the final example of this evening, or of this lesson. Now this lesson is kind of interesting. It was recorded for a Thursday class that I'm not going to be able to attend, to have a thing to attend to outside of class that day. So I'm actually recording this on a Wednesday evening, but that's neither here nor there. So let's work through a hinge example. And this is going to be interesting because we're actually going to need two free body diagrams. So let's get this. Let's go through, let's call this example 3. Here. So consider this beam here. And this is going to be a fairly interesting beam in that we're actually going to have more than 3 reactions. And in fact, because we have a hinge, we need more than 3 reactions for this thing to be stable. So I'm going to draw I first have a fixed support here. Then I have an internal pin or a hinge here. Then I'm going to show this along, have this beam going along. Then I'm going to have a point here. I'm going to call this point A. A hinge at point B. Then I'm going to have a point C. I'll need that later when I'm going to have a load on there. Then I'm going to have a roller at point D. And then finally, just for extra fun, all sorts of extra fun, I'm going to have a free end at E. So notice this is not a roller. I am not actually supporting the beam at all vertically here. This is just something that, imagine literally putting a great big pin in the middle of the beam. If I just have a pin hanging in space, that's not going to be able to support any vertical load unless it's actually lying on the ground. This thing is lying on the ground, although it's not an internal moment release. It's a roller support. So imagine having the beam, again, a roller would look something like this. Imagine having the beam look like this. This is a roller. This is what a roller would kind of look like. And this is what a pin would look like. A pin would look more, or sorry, an internal pin or a hinge would look more like this. So it's important not to confuse the two. Now I want to show the loading on here. Actually, first maybe I'll get the dimensions. Dimensions from A to B will be 8 feet. This is, of course, not to scale. And then 4 feet. 4 feet. You know what? Actually, I'll do a little better at making this to scale. I'm going to make this a little bit longer, just for accuracy's sake, or semi-accuracy. I never do try to make these to scale, but let's go ahead and make this a little bit better. And then this is going to be 8 feet out here from D to E. So 8 feet here. Now we're going to have some interesting loading. And here I think I actually will go and get the reactions, because getting the reactions here are a little bit complex. Let's say the loads here. Let's say I have, now, I would have, let's see, actually before I look at the reactions, let's show the loads. From here, I have a 2 kip per foot distributed load. A 2 kip per foot distributed load. Then I'm going to have a 10 kip point load pointing down at point C. And then I have a 12 kip foot couple at point E. At point E. And this will be all of my loadings. So all of this is given, except maybe this roller and hinge diagram. That's just something I illustrated here to show that. So all this is given, the full geometry of the beam and all of its loadings. And I want to find the V and M diagram. And this one, the shear, the reaction, getting the reactions is fairly complex. So in this one, I actually will go ahead and work through the reactions. Now, the first step is to get the reactions. Here. And I'm going to do this, is to find reactions. Now, this is going to be very important. We need to think back. We need to think back to what we did way earlier, toward the start of the year, when we looked at internal forces and finding whether things were statically determinate or not, and stable or not in frames and things like that. remember how we always had to break things at pins, internal pins? We have to do the same thing here. If you want to find the shear and moment diagram, you always, in fact, maybe I'll put it in a different color just for emphasis, maybe even write it in all caps. Always, I'll put it in nice rust or blood red or sort of a maroon. Hullabaloo, knack, if I got any Aggies listening. Anyway, always break at hinge. You have to do this. If you have a hinge and you are a beam with a hinge in it, you are always going to need to break it at the hinge in order to find the reactions properly. Every time, no exceptions. Well, I suppose unless the reaction's already given to you, but in any kind of real analysis, you always, forever and ever, amen, always break this thing at the hinge and see what kind of forces are revealed. So I'm going to break this. Instead of looking at a single rigid body, I'm going to look at two independent rigid bodies. So I'm going to have one rigid body here, the end here, and another here. And let's look at the forces. So I'm going to have AX, AY, and MX, or MA, sorry. AX, AY, and MA. The moment at A. Again, because this is a fixed support, I have AX, AY, I have an X reaction, a Y reaction, and a moment there. Then I'm going to have my distributed load, my 2 kip per foot distributed load all the way across, like this here. So a 2 kip per foot load. And maybe I'll go ahead and show the dimension on here of 8 feet. Now, I need to deal with because I basically cut the pin in half, I need to show the forces that are revealed. Now, I can assume they're acting either direction. It doesn't matter which way I assume they're acting, but I need to assume they're acting in some direction. And so, well, actually, what I'm going to do is I'm going to go ahead and assume the direction I know they have to be acting. Because think about this. I know there's a 10 kip vertical force here, and there's no other I don't know if I really want to assume that. Back up. Let's just say, I'm just going to go ahead and assume maybe that BY is negative here. That is, well, we'll see. I'm just going to go ahead and, let's just say, ignore what I said. Let's just say arbitrarily I assume that BY is negative, and so maybe we will assume properly, but we'll see. And let's just assume, then have BY here like this, and then a BX and a BX like this. So when I cut it, I reveal a pin, or when I cut the pin, I reveal 2 internal forces. Notice there's not going to be any internal moment revealed because it is a pin, but there will be 2 internal X and Y forces revealed. I can assume either way. I can assume there's an upward force here and a downward force here, or a downward force here and upward force here. I can assume either one, but it is absolutely 100% completely essential that I assume compatible loadings. I have to do this. If I don't, I'm going to get it wrong. In other words, if I assume this is acting to the right here, I have to assume this one is acting to the left. Now for this problem, it wouldn't matter because there's no horizontal loads, but the vertical especially. If I assume this one's acting downward, I must assume this one's acting upward. They have to be compatible with Newton's third law. Forces applied are equal and opposite. I can make this a little bit longer, because then the other force, I have another reaction, and that's going to be dy. There will be no dx because it's a roller there. So I have a dy, and then I have my end moment, or my end couple of 12 kip foot. Some nice English units after spending all that time in metrique. So let me go ahead and, just for extra emphasis, I'll even put a big circle around, big cloud diagram around all of this, just to really indicate equal and opposite. Never forget that. Equal and opposite. And I'll go ahead and label this free body diagram as free body diagram 1 and free body diagram 2, We cannot we cannot treat this as a single rigid body. We have to break this up into two rigid bodies and analyze them independently in order to find the reactions. So this 4 feet, 4 feet, and 4 feet. So now I'm going to next look at each individual free body diagram in order to get the reactions. Next, let us consider free body diagram 1. And at this point, I'm gonna ignore the pin and the roller and everything and everything else. I'm gonna look at a true free body diagram. Simply the actually, you know what? I'm gonna label that the other way. Sorry. I think I'm gonna call this one 1 and this one 2. Or actually, let me think about how I want to do this. Yeah, that'll work. I'm going to do this one first and then this one. And the reason for that is because if you look at the number of unknown forces, this is just going to make my life a little easier. If I do the free body diagram of this one first, I'm going to have a lot more unknowns. Here, I only have 3 unknowns, the B, the 2 internal reactions at the pin, and this dy, so I'm going to be able to directly solve for some things. So I'm going to call this one 1 and this one 2, and that's going to make things a lot easier. Otherwise, I have way more unknowns here. So it makes a lot more sense to do the right portion first in this case. So free body diagram 1, and I'm going to ignore the geometry, not the geometry, but ignore the fact that I have a roller, or ignore that I have a hinge in the middle, and I'm just going to draw everything as supported by just free forces. So looking at the forces, and I am going to make sure to put the same forces as I drew them. So I had a bx to the left and by upward here, so that's what I'm going to draw. Bx to the left and by upward. And I will go ahead and put my dimensions when I get those, because that makes things a lot easier to calculate moments and things like that. Then I have dy and my 10 kip downward point force and a 12 kip foot applied moment. And then my dimensions will be 4 feet, 4 feet, and 8 feet. Did I label that wrong as 4 feet? Oh, sorry about that. That was an error. It's 8 feet, not 4 feet. I was getting in the mood of 4 feet, so put 4 feet, that is 8 feet. Sorry if that confused anyone. So this will be 4 feet, 4 feet, and 8 feet here. So let's go ahead and get these reactions now. This is just statics. So again, this is point B, and let me go ahead and label the points. This is point B, and then C, point C, D, and E. Now, I'm going to go ahead and just do a sum of moments about point B. And this force and this force will not generate any moment about there. So I can just say, okay, well, it's going to be equal to 0, counterclockwise positive. So I'm going to have here negative 4 feet times 10 kips. Again, this is basic statics. Plus 8 feet times dy. And then minus 12 kip feet equals 0. And that produces a value that dy is equal to 6.5 kips positive, or 6.5 kips in the upward direction. Then I can do a summation of forces in the vertical direction, which will say that I'll have by minus 10 kips plus 6.5 kips equals 0. That's the dy that we already calculated, which leads us inexorably to by is equal to 3.5 kips upward. 3.5 kips upward, again, fairly trivial, just basic statics. Then the summation of forces in the x direction, I don't even want to work through this one. There's fairly obviously no horizontal forces on here, so bx is just equal to 0. We now have those reactions. Next, I want to work through the second free body diagram, the left portion of the beam. And my forces on here, let's just go ahead and draw this again with all the forces shown, including the reactions replaced as forces. I have a AX, an MA here, and a Y, and a by. Now, notice what I'm doing. I'm drawing it as downward. Even though I know that by is upward, that's on the right portion of the beam. And if it's upward on the right portion, it must be downward on the left portion. Equal and opposite forces. So here, I draw it as downward, and by is equal to 3.5 kips. And then I have my distributed load here. Constant value distributed load equal to 2 kips per foot. Equal to 2 kips per foot. And I can have my length, my dimension of 8 feet. So next, I'm just going to do a whole balance of moments and sum of forces. So first thing right off the bat, let's get rid of AX. This should be fairly trivial. Summation of forces in the x direction is equal to 0. That leads us to that AX is equal to 0. No surprise there. AX is 0. Then I can do a summation of forces in, let me go ahead and actually do a summation of moments instead of a summation of forces. Summation of moments about A is equal to 0. Because I like doing that, of course, because my AY will not generate a moment about that point. Let's see, I'll have the equivalent moment caused by the distributed load, or the moment caused by the equivalent point force of the distributed load. And that equivalent point force will be, have a moment arm length of 4 feet. It's applied at its centroid. Basically, the equivalent point force is 4 feet from the left-hand side, and its magnitude is 2 kips per foot times 8 feet, or 16 kips. So I can just say this is negative 4 feet times 16 kips. And then, again, this is going to be negative because clockwise rotation about point A. Then I can say minus the moment caused by By, minus the moment arm length 8 feet times the magnitude of 3.5 kips, and then plus my Ma, the moment applied at A, not applied, but the reaction moment at point A. All of it equals 0, and I get that Ma is positive 92 kip feet, or I could just leave it as positive, but I want to make clear that it's positive. Or I can just say this is 92 kip feet counterclockwise. 92 kip feet counterclockwise. And then finally I can do a summation of forces in the vertical direction. Summation of forces in the vertical direction. And I'll have AY. AY here minus 2 kips per foot. So that I have my AY, my vertical reaction at A, minus the force caused by the total force caused by that 2 kip per foot distributed load, 2 kips per foot times a length of 8 feet, plus 3.5 kips, and all of this is equal to 0. And if I do this, I will find that AY, not plus, minus, this is acting downward, so, if I do this and solve for AY, do a little algebra, multiplication and algebra, I get that AY is equal to 19.5 kips upward. So I now have all of my reactions. Now, you might think we still have a long way to go, but thankfully we actually don't. See, when we actually go, we do need to break things up when we're getting the reactions. We do need to break up when getting reactions. Do need to cut beam into 2 pieces when getting reactions, but we don't when getting the shear and moment diagram. I'm recording this too late at night. When getting reactions, but you do not when doing the shear and moment diagram by an inspection. You can, it won't really hurt if you do it properly, but we don't need to do that. So instead, I can now go back to treating the beam as a single rigid body, which means I don't need to worry about these reactions B here. Those will cancel out. All I'm going to need to worry about is the external forces. Because again, treat as rigid body, a single rigid body. Because remember, one of our first principles that we saw was that there is no jump in shear or moment at the hinge. So we shouldn't need to cut it. There shouldn't be any jumps there from the internal forces or from the force in the pin. So there should be no change in shear and moment there. So let me show what this looks like. Step 2 is going to be my free body diagram. And now it's just like what we've done previously with the method of sections, or sorry, with the method of inspection. So this is why I put the hinge example with the inspection rather than with integration or via method of sections. Although you could, of course, use any method for it. So the first thing I'm going to do is just draw a big, unified free body diagram. The pin disappears. I am now treating this as just a single rigid body, but I could go ahead and put a pin on there. But really, I'm treating this as a single rigid body. So I'm going to put all the forces that I have. Maybe I'll draw it like this. I'm going to have all sorts of trace lines on this one. So here, I have my 19.5 kip force here. And notice in my my large free body diagram here, my final free body diagram, I lose any distinction between reactions and loads. They're just loads. They're just forces at that point. It doesn't matter whether they're restraining the reactions or original applied loads. They're all the same thing as far as the beam is concerned. And then I have 92 kip feet here. And then I have a distributed load. I have a distributed load of my 2 kip per foot load. Distributed load of 2 kips per foot. All the way to the hinge. Two kips per foot. Then I have a 10 kip force here. Again, this is actually an applied force, but again, it's totally when you do the global free body diagram like this, the final free body diagram, the distinction between reactions and external loads is lost. Or not just necessarily lost, but it's irrelevant. Then I have my reaction here of 6.5 kips, and then I have my end moment, my applied end moment of 12 kips per foot, or not kips per foot, 12 kip feet. So notice there is no distinction between the reaction moment and the applied moment. They're all just couples at this point. Then I want to go ahead and put some dimensions on here. This is going to be 4 feet. This is going to be let's see, 8 feet, 4 feet, 4 feet, and 8 feet. Now, just like I had previously, so we can actually do this now as just a simple method of inspection problem. It's going to be exactly like what we've looked at before, no problem whatsoever. So I can do some trace lines down, and so we're almost done. Almost finally done with many long lectures of shear and moment diagrams. Finally, probably saying. At least if you're in my class and have been suffering through all of this long, detailed exploration of shear and moment, going well beyond what we usually do in, say, basic statics or even mechanics of materials. You should see if you're not in my class, you should see the homework problem I gave them for a method of integration. That one's a doozy. All sorts of fun things on that one. It's a parabolic load. Anyway, let's see. So, and we can see that if we tried to do this one via integration, oh boy, we're going to need 4 zones of integration, and that's going to be all kinds of headache. We could do it, but that's going to take a lot of time, and I am incredibly lazy, and if this is a relatively simple loading, so guess what? I can very easily do this via inspection, so I'm going to go ahead and do that. So step 2 is going to be our V, and I'm going to label this in kips here. And I'm going to draw my 0 line here. It isn't quite horizontal enough for my taste. Good enough. And I know these are all just rough sketches like most of the things we draw. So the first thing that's going to happen is I'm going to need to note that our couple here is not going to change any, is not going to produce any change or jump in our shear diagram. Just like we saw previously, couples do not, or applied point moments do not, I repeat, do not produce any change in the shear diagram. Common mistake, and I can pretty much guarantee someone will do that on the exam, but Oh, well, he had been warned. Okay. But what is going to happen is our reaction here, our upward reaction, our point force here, this is going to cause an immediate upward jump of to 19.5 kips as an initial value for our shear diagram. Now we want to look from point A. You know what? Let me go ahead and label some points so I can reference these as we go across. And they're simply named, of course, point A, point B, C, D, and E. So looking at an area approach, I know that from A to B, the shear is going to drop by an amount equal to the area under the load curve. And in fact, this is actually going to be the only thing that has any, this is going to be the only area under the load curve. And it's going to drop by a total of, well, 8 times 2 is 16. And so I know that we're going to drop down to 3.5 here. 3.5 here. And because this is constant value, the integral of a constant value function is linear, so we know we're going to drop down via a linear function here. Then from B to C, I have no load, therefore my shear function is my shear plot is going to be constant. Again, the only thing that can produce a change in shear is my load. I have no change in shear. I have no load from B to C, so therefore I have no change in shear. Now, at point C, I have a point force, and that's going to cause a downward drop in the shear. And so 3.5 minus 10 is going to, again, the point force is going to cause a drop equal to its magnitude, and it's a downward force, so it's going to cause a drop, and 3.5, it looks like a 3 point something, 3.5 minus 10 is going to be negative 6.5. So negative 6.5. Negative 6.5 here. Then from B to C, what kind of load do I have? Well, I have no load there. So that means from B to C, the shear is going to be constant. Then finally, at point D, well, not quite finally, at point D, I have a vertical force or a vertical reaction, whatever you want to call it. And an upward force is going to cause an upward jump in the shear. So that means I'm going to go up to 0. I have no load from D to E, which means it's constant. And hey, what do you know? I end up at 0. So maybe I could even indicate that there's 0 here. And in turn also, I have to stress one last time that this couple here, or this point moment, whatever you want to call it, is not going to cause any change in the shear diagram, so it's okay that we end up at 0 and we just stay there. These will affect the moment diagram, but they will have no effect on the shear diagram. So I want to go ahead and get a couple areas, so I'm going to do that. I'm going to give these a couple of colors. First, I'm going to get the area of this first trapezoidal thing, and we could do that just in our heads or in our calculators, but I'm going to go ahead and label this. So, and do the little calculation to the side, A1, because we know the area under the shear diagram will indicate the change in the moment diagram, so we're going to need that. So area 1 here, let's see, this is just going to be a triangle, an area of a triangle, plus the area of a rectangle. And the area of that triangle is going to, oh, I lost my page here, is going to be, the area of that triangle is going to be 1/2, and the height of that triangle is going to be 19.5 minus 3.5, or 16. 16 kips times a length of 8 feet. So that's going to be, again, the area of that triangle, just this the top triangle here, 19.5 minus 3.5 is 16. That is where that 16 kip came from. And then plus I need to add the area of the 3.5. So plus 3.5 kips times an area, times a length of 8 feet. And that comes to 92 kip feet. 92 kip feet. Huh, interesting. It's exactly equal to the 92. I wonder if that's a coincidence. Nope, it's not. Then I want to label some other 2 areas. Oh, let's see. Maybe I can label this one. Oh, what color do I want to use? Maybe purple for the next one. Let me call this one area 2. Now you don't need to do the separate calculation. I just want to do this so you can see very clearly what all this is coming from. Keep jumping forward here. Sorry about that. Area 2, so just a symptom of the tablet I'm using. Probably should find a way to turn that off. But anyway, area 2 is going to be fairly easy. It's just a rectangle. This is going to be 3.5 kips times a length of 4 feet, and that will come to 14 kip feet. Then let me get my third area. And let's go ahead and use some light green here. This area will be area 3. And area 3, again, is just another rectangle, except it's going to be negative. So I'm going to put negative 6.5 kips times a length of 4 feet. And that'll produce an area, man, just keeps wanting to jump forward, an area equal to negative 26 kip feet. Negative 26 kip feet. And now our moment diagram is going to be relatively simple. Not cake, but well, pretty close to cake. Relatively simple. So step 4 and the final step, and the final bit of this entire long unit on shear and moment diagrams. Get the moment diagram, in kip feet. And let's have a 0 line here. Now we need to figure out where we're going to start. And we're going to start down at negative 92. How do I know this? Well, I know that a positive moment, a counterclockwise moment, will produce a negative jump in the moment diagram. So we're applying a positive moment on the outside. That means the internal force must start down at negative 92. Then notice the area 1 is positive, which means we're going to increase up here. We're going to increase by a total of 92. Negative 92 plus 92 brings us to 0. Interesting. Brings us to 0. Oh, and wait a minute. What did we say about hinges? Moment equals 0 at hinges. A hinge cannot resist any moment, so it makes sense that we should get 0. And I didn't just start there and assume it. We actually worked through it by the calculation. So we know this is a useful, just like working your way across a simply supported beam and finding the moment at the end is 0 is a useful check. This is also a useful check. If we did this and we found that the moment was not 0 at the at the hinge here, we would know that we had done something wrong. Now, we're going to need to figure out something like that. In fact, maybe I'll just go ahead and even put a little label here, just for extra emphasis, or emphasis if you prefer. Here, moment is 0 at hinge. I know it's kind of light. I'm kind of trying to use some different colors here. Moment equals 0 at hinge. And now the only other thing I need to figure out between A and B is what kind of function is it going to be? Well, I know it's going to be parabolic, and the only other thing I need to think of is, okay, well, what is it going to be? Is it going to be concave up or concave down? Now, it's not going to have a 0 slope at this point because the shear doesn't have a value of 0. However, I do know that the slope must be decreasing in magnitude. It must be decreasing in magnitude because the value of the shear is decreasing. So it should be steeper at end A and less steep at end B, although it should never actually equal 0. So it should go something kind of like this. It doesn't actually equal 0, but it does become less steep as we go. It's sort of flattening out. And I'll go ahead and put a P here to indicate parabolic. And maybe I'll put a little note here just for us. Here, a little note here showing that shear decreases, therefore slope shallower. Of M, maybe of M shallower. Actually, you know what? I don't like putting this here. It's going to take up too much space in the diagram, so I think I'll just put that I do want to have that in the notes as a little asterisk so you can remember where this is coming from. So I'm just going to put a little asterisk here. And then to the side here, I'm going to say that asterisk is that the moment diagram, the V decreases in value or in magnitude, becomes closer to 0. In magnitude, therefore, M becomes shallower. Just a relationship. All it is, of course, is a very straightforward application of the truth that the dm dx, the derivative of moment, is equal to the shear. Okay, then we're almost done of this long-winded explanation for something relatively simple. Then I know from B to C, we're going to increase by an amount equal to A2. It's still going to be a positive increase. So I know it's still going to be a positive increase because the area is above the axis. And I know the area is 14, so that means we're going to increase by 14, which will put us at 0 plus 92, or sorry, 0 plus 14 means that we end at 14 here. Then the question becomes, what kind of function do I have? Well, I know that the integral of a constant value function is a linear function, so that means it's going to be linear from here to here. And if I were to draw this exceedingly accurately, I would make sure the slope of the endpoint this was the same slope as we had all the way across. So we just have a slope, trying to get it as constant as we can, but not going to be able to exactly get it. Well, actually, I suppose I could just go and erase that and say we're there at 14. Not to scale, not scale, not scale. So we're at positive 14, and I'll go ahead and put a L here to indicate this is linear. Then I want to get from B to C, or sorry, C to D, and I know that we're going to drop down a total of 26. So if we were at 14 and we drop down to 26, 14 minus 26 is negative 12. So we're down here at negative 12. And just as before, because we have a constant value function between these, maybe I'll put this over to this a little bit further down. Because we have a constant value function here, the integral of that is a linear function. So this is going to drop down as a linear function. We have that there. And finally, the moment here from here to here, well, from D to E, we have no shear. There is no shear in the beam, which means there is no change in the moment. There's still moment, but there's no change in the moment between D and E, because the only thing that can produce a change in moment, besides an end moment, besides a point moment, is a area under the shear curve. There's no area under the shear curve, therefore there's no change in moment, which means moment is constant all the way across at negative 12. And hey, what do you know? We have a negative moment applied at the far end of the beam, at the cantilever end of the beam. And we've already learned that a negative moment, or a negative or clockwise moment applied to the outside of a beam is going to cause a, that's not horizontal enough for my taste, a little bit better. We already know that a negative or clockwise moment applied to the outside of a beam is going to cause a positive jump in the internal force in a beam, or internal moment. So negative 12, so in other words, this will increase by 12 kip feet, and negative 12 plus 12 will bring us right back to 0. So we are good. This is going to be our final sheared moment diagram here, our final moment diagram. Oh, and maybe I'll just put a note here that this is linear, and of course this is a constant value function. If you're ever doing a sketch, it's very useful, because often it's difficult to tell whether you have a linear or a quadratic or a cubic function or something. But especially when doing rough sketches, if you're doing an exact plot of a computer or by very precise points, it's easier to tell. But if you're doing a sketch, it can be very difficult to tell sometimes. Anyway, so it can be useful to actually indicate whether you have a linear or a parabolic or a cubic function just by a little note like this here. Anyway, that concludes my instruction here, my lessons on all the various ways of finding shear and moment diagrams. So we've looked at all sorts of different ways and really complex forms of finding shear and moment diagrams, both via method of sections, via integration, and finally now today via the method of inspection. I hope you enjoyed all these lessons. I hope you learned a few things. That'll do it for today. And as always, thank you.